Hey, welcome back to Chips and Salsa, where we talk about security and intel. I'm Jerry.
I'm Krobe.
Hey, Crow, we got a great show today. We're talking with Ram Chari about Intel threat detection technology. So, hi, Ram. Thank you for joining us here on Chips and Salsa. Can you just give us a little background about yourself, how you got to Intel, and what you do here?
Great to see you both, and hey, thanks for the opportunity to talk to you folks today.
Very
Really
welcome.
appreciate it. Yeah, my background is, I have an undergraduate degree in physics and then double E, and then I got into software, in college. And right after, there's only one company I actually wanted to work for, which was Intel. So I came to Intel right after college, and I've been here the whole time. It's always working in this confluence of hardware and software, which keeps me excited. Keeps the whole thing exciting. It's really good. In terms of what I've been doing, the thing about Intel is we work on so many different technologies that I've really blessed to have had the opportunity to start out at the microcore level, at the CPU level. Then I worked in networking, worked on PC power management, and the last few years I've been working on security. And one of the fun things about it's great, and one of the fun things we've been doing is just the technology we developed, but also the opportunity to work with some great partners. Both the really big ones as well as a lot of small companies to bring our vision of security collectively to the end user. So it's been great.
Mhm.
That's awesome.
Yeah, it is. And you're here today to talk about Intel Threat Detection Technology, or TDT.
That's right.
So, what are the challenges that TDT is trying to set out to address?
Okay, as you'll see in this slide, you basically see the proliferation of ransomware. In fact, over the last 2 years, has been dramatic. There have been a lot of attacks, and for example, there are some very big ones like the Colonial Pipeline attack that you've all heard of. But it's not just the big the national infrastructure, right? But a lot of times it's the small school districts and the hospitals. This actually is hitting a lot of real people and causing some real damage. And there are a couple aspects. One of the questions is when we ask, why is this happening? Right? There are two aspects to it. The first part is just the proliferation of ransomware is very big. But the even primary part, which is not just unique to ransomware, it's common to all malware, is just evasion techniques, right? They have been evolving over time too. And we'll touch on it briefly, right, just to see why this ramp is happening. Historically, evasion, the way you detect a lot of attacks, our AV vendors, antivirus or endpoint detection and response, or EDR vendors, they would be looking at signatures, right, of various types of files that are on the hard drive, and that's what we historically used to see. But this is a cat and mouse situation, right? So malware has changed over time, has adopted to this thing. And these days, you see a lot of malware, or they're not even on the hard drive. They're what they call, they're fileless attacks. They are in memory, and they are getting very difficult to detect just with signatures alone because they morph themselves a lot. They're called polymorphic. They change a lot. They use a lot of encryption techniques, as you folks are aware of, to hide themselves. And in fact, some of them that's what's a lot of things have been happening. It's kind of intensive, CPU intensive to kind of try to detect them as well in memory. And some of them live off the land. They use this return-oriented programming or ROP attacks where they kind of stitch together real code, actually good code that's in memory, and come together with an attack. So, of course, our partners have evolved. Of course, they've evolved their detection techniques, and today a lot of our partners use behavior analysis using software. So, for instance, you can look at what kind of system calls are being made by various programs, so that you can try to tell, and you have some odd behavior to kind of indicate that this could be a malware because it's making a lot of strange sets of calls. Now, of course, malware has been adapting to that. And one of the things that a lot of malware has done is some techniques like process splitting. So let's say when a ransomware attack is trying to encrypt, let's say, 1,000 files on your system, rather than one process going and doing 1,000, they kind of split themselves into, let's say, 10 smaller processes. Each of them are encrypting just 100, but the goal is to kind of blend in with the rest of the good guys, so detection becomes an issue. And some of them have even taken it to the extreme where they can run within a virtual machine or a VM. And so now if you're one of those, good guys, AV programs that's running on the host OS, say Windows or Linux, anything that's running within the VM is, it's opaque. So you know something's happening. You can't really detect what's going on. So that's kind of the evolution of, the way attacks have been going in general. And the last piece I wanted to mention is, like I said, the proliferation of, which is very unique to ransomware, because it's so easy to make money out of it. These days, ransomware has moved to ransomware as a service model. So where, let's say if somebody were to, put together an attack, they can go to one website and find the attack vector. They can go to another website to find, what are the gaps in a particular organization. They can, the third website to come up with a deployment mechanism, and the fourth website to go through a monetization part, right? How do you actually get the money? So it's made the bar of entry pretty low. So you're seeing a whole lot of new variants, and that's why the number of these attacks have also gone up dramatically over the last couple of years.
Mhm.
Yeah, that's for sure. So at a high level, how does Intel threat detection technology address these challenges?
Yeah, thanks. Yeah, the thing that we've been doing is we talk to a lot of our partners, and one of the things, they've been doing great work, right? They do great work in detecting so many of the attacks. But the feedback we got from them is, we detect most of them, but some of these attacks do get through. And their request was, is it something that Intel can do by using some of the hardware capabilities to be able to close that gap, right? So we can get more proactive in how it kind of augments all the software-based behavior analysis that our partners already do, so that you're getting closer to the point where you can detect the attack as soon as it happens. So that's the request that we got from them. And of course, they want these attacks to be detected in a couple different ways, right? The first is, ideally you want it to be as effective as possible to detect all these variants or evasion techniques that I talked about, whether it's running a VM or process splitting. The second thing, of course, is you want to reduce the false positives for any of these types of things, because anything that's, a good signal is very important, but if there are a lot of false positives, it becomes, not very useful to our partners. And the third part that they've been asking us, of course, is they're all running under very tight CPU budgets, right? Nobody wants to be the CPU hog that all of us hate as users. So they have some very strict kind of headroom requirements for us. So in our case, they said, well, it's great if you do all those things, but while you're at it, you want it to be under, say, 1 to 2% of the CPU, so that it's running all the time and there's not a perceived overhead if you're the end user.
Mhm. Well, that's a great overview. Could you maybe go a little deeper and kind of explain how TDT is working under the hood?
Oh, absolutely. So we kind of looked at those three different aspects that I talked about, and looking at our hardware in terms of how can we address those concerns. The first thing was, the efficacy part, right? How do we actually try to detect these evasive techniques? But the good thing is, ultimately, independent of how evasive it is, it can be hiding in a VM, it can try to split itself. But at the end of the day, for, say, a ransomware to be effective, it has to be able to encrypt files, as one of the key things that they do. And which means it has to run on the CPU. So our focus from day one was, and then while we are talking about ransomware today, the same technique we have applied to other types of attacks, or crypto mining attacks, are very similar. That's a problem because you'll have a crypto miner running on your machine, and sometimes they run in a VM, and it's impossible to detect that. All you know is there's a CPU overhead. You don't know why it is. So that's the goal was, can we detect this runtime behavior ultimately when it's running on the CPU? And the great thing is in our Intel CPU, and this is true for our PCs as well as on the server side and IoT across the board, we have this great feature called a performance monitoring unit, or a PMU. And what the PMU really does is, at the microarchitectural level, it's tracking hundreds of, think of it as microarchitectural behavioral events. So for instance, it could be a cache miss is an example, a branch mispredict is another one, and there are literally hundreds of these ones. And the reason they've been there historically is because, as developers, as we develop code, you want to be able to optimize the code to see where are the hotspots in terms of performance, so that you can kind of zoom in on those and try to optimize. So usually this data gets fed into, Intel has a tool called vTune for that purpose, and there are other software packages like that, so that as developers, when we run the program, we can actually tell, okay, this is where it's pending. There's a lot of loop inefficiency that I can try to fix. So that's the background for why this feature exists. But we kind of turned it on its head and said, ultimately, like we said earlier, any attack, malware or otherwise, that's running on the system ultimately is software. So it's going to leave a fingerprint at the CPU microarchitecture level. So our goal was to try to use a subset of these events to see if we can uniquely, say, figure out if it's a crypto miner or it's a ransomware. I mean, there could be different types of events, but can we detect that using a small subset of these events? And the good news is we were able to do that. We started out, some years ago with different attacks, and we tried the crypto mining, which was quite successful. And then when we went to our partners, we said, well, ransomware is the big one. Can you solve it? And we did. And working with our partners very closely, we've actually deployed that over the last year or two. So that's the first part, right?
Mm-hmm.
And as I said, the advantage of this technique is using something like the PMU is we are tracking, by the way, this microarchitectural criteria, the behavior is tracked at a thread level. You can track it at a process level, at a thread level, a very fine granularity. So even like I said earlier, an attack where the fork itself off, kind of process split itself, we will still detect it because it runs on the CPU. If it's running within a VM, ultimately it's going to run on the CPU. And so it's a crypto miner, for instance, we can detect it when it runs right away. So it's a very powerful way. And since we are at the lowest level of execution, there's really no good way to bypass it. So it's been a very effective tool for us to detect it and try to get that signal to our partner. Now,
that's amazing.
Yeah, it's a very powerful feature. Now, as I mentioned, that's the first part, the efficacy part. Now, of course, the second thing is you got to be able to address the false positives too, and this is where I think the use of ML has been very powerful use of ML with TDT, right? And the picture that we are actually going to share with you is of a crypto mining detector that's actually that we actually built a machine learning model for, right, as you can see right now. Now, in this particular case, for detecting something like, in this particular case, a Monero miner for just for information, and this can be detected. Like I said, there are hundreds of events, but we only needed 3 different events to be able to detect this, and those are kind of indicated in those 3 axes there. If you the way we train these machine learning models, of course, is you feed it the bad guys, of course, but you also have to feed a whole lot of benign apps, because the more your sample size is, the more accurate it's going to be. Now, if you look at this picture, every dot on that is a different process that's running on that CPU at any time. And as I mentioned earlier, these events are it's something the CPU tracks, and all kinds of applications can trigger it, right? So both the good guys as well as the bad. The key here is to be able to see if there is a unique way in which the bad guys here, in this case a crypto miner, is using it, so that we can say, okay, that's what it is. And so our models are actually designed so that once you feed in all this data, if you think of this as a cake slice, the icing is the bad guy, the red layer is the bad one, and everything below that is the good stuff, right? It's the cake. It hurts me to say it because I love the icing too, but in this particular case, the icing is the bad guy, right? So once we detect, and now we have figured out this model, and it's, let's say, deployed on all our machines, and 2 months down the road, then it's detecting a behavior where something is falling on that red level. Now this machine learning, the whole algorithm is going to say, okay, this particular process is behaving like, say, in this case, a crypto miner, right? And we can immediately give that within milliseconds, right? We can actually give that information saying, hey, this particular process or VM And we give that handle to our partners so that they now, as soon as it happens, they can do, the remediation part, right? That's what they're really good at, and they feed it into the larger signal, intelligence that they have on the system. So we work very closely with our with our partners to be able to deploy it, because they have the wherewithal to do the remediation. So our focus is primarily using it for the detection technique. And the last piece to mention there is, as I said, performance is a very important part. That this one takes 10% of the CPU. It could be great, but nobody will deploy it. And this is where there's another great feature that's in our CPUs on our PCs, for instance. You have this excellent integrated graphics, integrated GPU as we call it. And a lot of times the challenge with machine learning, of course, is machine learning is CPU intensive, right? The more models you run, the more trees that you build in terms of the machine learning model, the CPU consumption goes up quite a bit, and that kind of impacts our end user. Suddenly you see 10% of the CPU. That's not good, right? It takes away from our use of the system. But the great feature is now the machine learning models that I showed in that previous slide, we don't have to run on the CPU. What we find is we can offload it to this integrated graphics that's right on the same die. So the latency is very low. But what it actually gets us is now what would have taken, say, 8-9% of the CPU can now run for less than 1% of the GPU, right? It's almost, because the scale of the GPU has, sometimes 64 parallel execution units. And the other side of the other benefit, of course, from a CPU perspective, we can run these models. In fact, I can run all these models, crypto mining and a ransomware attack detector, all of them in parallel, and still use up less than 1% of the CPU. So for us, it's a good way of using, you can have the security without the performance impact, which is always the big goal that we are all shooting for. So that's, in a nutshell, that stack is TDT, right? And it's on our Intel PCs.
That's pretty outstanding, actually. Where can security vendors learn more about Intel threat detection technology if they want to incorporate it into their product?
Yeah, fantastic. We have we're a big company, but we are a small team in a big company. So, but we are, just send me an email, and I work very closely with our business unit folks. We are part of the same team, and we already have. By the way, there are some, I think, links in our website that we can share. We can share down there. It'll be down there, and we will. That gives you a lot of information about TDT and the the various components and the architecture that we have. And we'd love to work with our partners, and we've been talking to many of them, but we're always open to talking to the very extended set of folks that we work with.
Mm-hmm. So, what's next for TDT? What you shared today is amazing, but where could you take this next?
Yeah, no, that's great, right? That's what keeps us going every day. I would say a couple different aspects, at least, I want to leave with. One is I was talking about. Bringing more machine learning to the platform. And if you broaden it, it's actually how do we bring more AI? Say if you want to bring deep learning to the endpoint, where do you run it? Now we can definitely run it on the GPU, but our desktop, our PC CPUs, if you look at our roadmap, we have it's called a VPU, which is a versatile processing unit. It's a very dedicated silicon that we have put into our future chips, and now we can run much more. For instance, we can run neural networks, right? So we can do other things with the goal to minimally impact the CPU, because we have a very focused high performance accelerator. So we are starting to work with our partners to kind of up the game, right? Not just in addition to doing everything we're doing. Can we use some of these neural network techniques to make, again, keep raising the bar on detection and how we can get very proactive. The other part that is kind of interesting is kind of progressing along the lines of how do we use our PMU that I mentioned. Right? So today, a lot of the things I talked about TDT as it is today, it's focused on known attacks, right? For instance, you have it's a crypto mining or ransomware attacks. These are families of attacks that you kind of know, or of course there are a lot of new variants, but you're looking for a specific bad guy. And of course, we want to get closer to a zero-day attack detection where you will know who the bad guy is, right? Our goal is, if you take one of those good guys, if you take an application, a good application, it could be you're one of those companies where this is your, CRM or your mission-critical application or database, whatever it is. We kind of run it through a profile. We use other features in this PMU where you can look for the control flow graph or the execution graph of this application. So, for instance, you run it, in a lab in the background, and you can tell all the paths that your good application normally takes, right? And so that's your known path. And now you deploy the application, and you may have attacks like supply chain attacks that we have seen. Or it could even be something like a performance issue, right? Not necessarily a malware attack, but something happens, down the road where the behavior of your application suddenly changes, right? It's starting to make certain calls, or it's calling to a server that you've never seen it call before. And a lot of them are inklings of some of these attacks because that's what they do. They stay dormant for a while and then they connect to the backend to start pulling a payload. So we can detect that anomaly. So that's our anomalous behavior detection using our CPU techniques. And again, we can give our partners immediate notification saying, hey, this particular application is doing something strange. And then they can run a lot of the other, they can then, isolate that system or detonate that application in the cloud. They have other techniques to kind of debug that, why that is the case. So in my mind, I think of it as the engine light in our car, right? So it's kind of programmed to certain execution parameters, and when that exceeds, you get that engine light, and then you take it to the mechanic to kind of debug it, and they can figure out what exactly is happening. So that's something it's fairly far along. We've actually had some technical papers. Again, the links you'll see below. But we are actually actively starting to work with partners to be able to deploy that over the next, in the immediate future. So that's the other thing that it's been fascinating technology.
Well, yeah, I think we talked about this once about how that's going to be so practical and relevant for supply chain attacks,
Absolutely.
where software update mechanisms are compromised and malware installed into those updates, and those would be detected right away. That's pretty awesome.
Yeah, thank you. Yeah, that's what again, working with our partners, it's been a great collaboration, and at the end of the day, we want to deploy it so that our end user doesn't need to know. It just automatically, you buy as we buy our new systems, they get progressively better working with our partners.
That's great. Well, Ram, we're really excited to see what is next for Intel threat detection technology, and we really appreciate you coming on the show today to tell us about it.
Thank you.
Thank you so much.
Wow, that was a really excellent conversation. I learned a lot about TDT today, Jerry.
Yeah, this is super cool. Having spent a lot of years, working alongside the malware industry, this is one of the most exciting things I've seen in a long time.
Yeah, I agree. I had the chance to talk to one of my mentors recently at a security conference, and he mentioned he specializes in post-incident breach remediation. So he works with people that are victims of ransomware. And he mentioned how the ransomware industry globally in 2021 was like a $5 to $6 billion a year industry of profit.
Yeah,
Crazy.
Yeah, people getting jobs at ransomware companies, that kind of stuff.
Yeah. So hopefully, things like TDT and working with our industry partners helps kind of alleviate some of this pain of that problem.
Yeah, definitely. Well, that's it for this episode of Chips and Salsa. Thanks for watching.